Okay, so this is the rate of change of concrete volume during a 30-second pour. We're pouring the concrete, and this is tracking the rate of change over about 35 seconds. And our task here is to make a sketch of F, the accumulation of concrete during the pour for that same time frame, and write a function that gives that accumulation function exactly. So go, take about 3-4 minutes to do this.
That makes a lot of sense. Thank you.
So let's actually do 2 first. How many people think they can do part 2, which is write the function f? How many people think they can write the function f? It was like the whole first month of class. Did we learn anything this semester? How many people think they can do it? Anthony, thank you. Riddick, thank you. Anybody? Chris, tell me.
I put the integral from 0 to 30 of the rate functions. I put t to the 4th, e to the negative 2 over 2, dt.
All right, what do we think of this here? So you said t to the 4th, e to the minus t over 2? And then dt? Okay, what do we think? 30 has to be an x. What does it mean that it's 0 to 30? What do you get when you do 0 to 30? That's something that's relevant. That is something. What is that? What could you say that is?
Function value.
And what is that in the context? The function value. Yeah, and what's that? The net accumulation from 0 to 30. What's that in this context? Total, it's the volume of concrete at 30 seconds, right? So all the volume of concrete that's been poured at 30 seconds. So I'm glad you said that, because this is a common thing that students do, so we could talk about it. So this isn't a function, it's really just that one accumulation value for 30 seconds, the volume of concrete at 30 seconds. So instead we want, ready? X. Now what's this? All the volumes of concrete for any value x. So we have a function now, right? So we could plug in x equals 1, and we get the volume at 1. X equals 4, we get the volume at 4. So the idea of a function that we can any final value of time and get the corresponding, it gives the corresponding volume of concrete. So let's graph that. And so what did you think this graph is going to look like once we graph it? Draw it with your finger in the air. You all got it. So is the volume going to go back down now? Why doesn't the volume go back down? Still accumulating. It's just you're accumulating at a slower and slower rate, right? It's a positive rate the whole time. If it's a positive rate the whole time, the volume always goes up, increases, right? Goes up, increases. Okay, and so what about finding, someone said, do you want open form or closed form for the accumulation function? What about finding closed form for this? Okay, and how do we do that? Antiderivatives. So this is now the second month of class. How would we do that antiderivative? What's it? Undoing the product rule or undoing the chain rule? Anthony, is it undoing the product rule or undoing the chain rule? He's going product. He's sticking with his initial answer. This would have to be to what power for it to be undoing chain? Fifth. You need fifth power here. So we're doing undoing the product. And tell me about that process of undoing the product rule in this problem. What's that? Yep. So f would be t to the 4th, and g prime would be this, and then what would happen? Remember? T to the fourth and e to the t. You want to do it? No, you don't. Why not? What's that? 4 times, right? Remember, this is because this is the power 4, you end up have to do it 4 times. Each time you reduce the power of t, you get another integral that you keep doing the product rule on. So this would be nested. That process would be nested 4 times. Okay, remember that? Remember that? Okay. All right, so this handout. So now what I want is, I want to take this information from these 2 graphs. So you're working on the page that looks like what we're working on with those 2 graphs. Okay, so now what I want to do is I want to create a new function, and this new function is I want to know the rate. I want a function that gives me the rate of change, but no longer as a function of t, but as a function of the volume port. So given the information you have from these 2 graphs.
I have more than.
Oh, is there more? Given the information from these 2 graphs, I want to try to come up with a function that gives me the rate as a function of the volume that's been poured. So any way you can do it, figure it out. So how can you come up with a graph based on these 2 graphs of rate of change versus volume poured now on the x-axis, on the horizontal axis? Go. So if you need to confer with each other, that's fine. So for the units on the y-axis, meters cubed per, oh, it's minutes, not seconds. Meters cubed per minute. And then meters cubed on the horizontal axis. So how are you going to create that graph from these 2? Okay. 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 Right. So he looked at, so for a volume of 100, you found what? Where's the?
It's 100 meters cubed at around 5 minutes. So if you go 5 minutes on the left graph.
Kind of more like 7, right? The 200, thank you. All right, so 100 would 5 minutes. So 5 minutes gives us a volume of 100, and it gives us a rate of 70-ish. So then you can come down here and do what? Right. Is it 70? Am I in the right place? And that's because that came from what? That came from t equals 5 minutes, right? So for t equals 5 minutes, we can get a point on that graph, the volume and the corresponding rate at that time. So I got to animate. Is this kind of what you did? You can pick different points in time. For each point in time, you can get the 2 values you need, your independent or your horizontal volume and your vertical rate of change. So let's watch this. Oh, where is it? I had it open. It's gone. There's t equals 5. So for t equals 5, find the volume, find the rate, put your volume on the x-axis, your rate on the y, horizontal or vertical coordinate, it gives you a point. All right, t equals 7. Got the rate, got the volume, put the volume on the horizontal axis, go up from there, the amount of the rate gives you another point on our new graph. So this is the new concept that we're starting in for the next week or two. This is the idea of a parametric function. So how is this different than the functions that we've been dealing with, like these individual functions? How is it different? So it's different. It's different in what we are modeling as the independent and the dependent thing. So in this new function that we're making, what is the independent quantity or quantities? What's the independent quantity or quantities in this new function that we're making? The volume? And what's the dependent thing? Okay, so if the independent thing was volume and the dependent thing was rate, how is that any different than any function that we've ever done before? Is that the same or different? That's the same. So that's not viewing this parametrically. The way we view this parametrically is the way that we're constructing this function. All right, so what's independent and what's dependent in the way that this thing is getting created. It's not that we're taking values of volume and getting values of rate. That's not what we're doing to create this, right? So the way that we're constructing this is the backbone of what a parametric function is. So what is the independent thing in this function? Time. We're starting with a time, right? Start with time equals 13. That's the independent time in minutes. Does that get graphed? Does time get graphed? Doesn't get graphed. It's kind of behind the scenes, right? It's behind the scenes. It's not on the horizontal or vertical axes. But in the parametric function that we're creating, it's the independent thing. We start with time. What's the dependent quantity or quantities? Volume and rate are dependent. See, now this should feel a lot different than the functions you're used to, right? This graph, both the horizontal axes and the vertical axes are showing the dependent thing, right? So the dependent thing are ordered pairs taken together. So this is what? F of 13 and R sub F of 13. The dependent entity of this function is now an ordered pair, not a single value. And that ordered pair is dependent on time, the independent variable. Okay, does it make sense? Does this idea make sense? So we don't graph anymore. We're not graphing. We don't have an axis for time anymore. Our axes are showing the two values of the dependent variables and ordered pairs for every given value of the independent variable, which in this case is time. Yeah, Nick?
Since they're both dependent variables, could you flip the value of the f and rate?
Yeah, absolutely. So if we wanted to show, we could have shown volume on the y-axis and rate on the x-axis, and that would have been fine. It's a very, very similar but different parametric functions, switching where we put those. Yeah, it's totally valid. So other questions on the idea here? So now I want to go back to GC and I want to graph this. So is this paused? No, it's done. So yeah, so far we made a bunch of points, right? So we made a bunch of points. We get something like that. So then we want to think about this thing varying smoothly, right? It's not just a bunch of points, but as time varies smoothly, these ordered pairs are generated smoothly. So this is what this looks like. So as time increases smoothly, then all possible values of this function or the curve are generated. So it helps to plot points to start to see how we get it going, but then this is the way we want to think about it. Time varies continuously, and so we get all these ordered pairs generated continuously. And so there's that graph that we were after. Rather than just 10 or 20 points. It's an infinite number of points, right? So I want to graph this on GC, but I want to now tell GC to graph it parametrically. So let's see how we do that. So we got our function. I'll copy over my functions here. So I got the rate function. And I got my accumulation function. So now I want to graph this parametrically. So the way that I do that is if I hit Control 2, it gives me what's called, this is a two-dimensional vector. And so this two-dimensional vector is going to assign points. This is, so you've seen this before. This is just plotting a point, right? So this is what a parametric function is. It's plotting a bunch of ordered pairs. So the way I'm going to do that is I'm going to say equals, and then do it again, Control 2. And so what do I want all my x values to be? Rf of t? F, right? So f of t. And my y values are sub f of t. So now we're telling GC to create that graph that we've been working on, putting what? Putting values of f on the horizontal axis for x values and putting the rate on the y-axis for given values of t. So let's graph it. And what happened? So if you noticed over here, it shows t varying from 0 to 1. Is that what we want? What do we want? 0 to like 35 or something? So now I'm going to change. So instead of showing all the points as t varies from 0 to 1, I'm going to show all the points as t varies from 0 to 35. And we'll zoom out. And then we'll zoom out on the... And there it is. So this is how, so we're telling GC to graph this parametrically. As t varies, we're going to plot x coordinate as volume and y coordinate as rate. And it gave us all those points. So now let's suppose I want to make this t to 0 to 1. Why might you want to do that? I want the whole graph to show, but I want t to go from 0 to 1 because maybe I'm graphing several parametric functions and they all have kind of different t variations to them. So I want this kind of universal, easy range from 0 to 1, right? It's a very convenient range. Start at 0, end at 1. And so how can I adjust my function now to show? So you can't even see, as t to 0 for 1 is so small you can't even see what's going on there. How can I adjust my function so I can still see the whole graph that we saw before? As t goes from 0 to 1, but I want to show all time values from 0 to 35. Any ideas? Yeah. What's that? Yeah, so as this t here goes from 0 to 1, this thing's called the argument, right? This is the argument. We need the argument to go from what to what? 0 to 35. So how can I adjust the argument so that when t changes from 0 to 1, the argument will change from 0 to 35? What can I do to the argument? How can I adjust that right there? If I multiply by 35? So now what will happen as t goes from 0 to 1? What about what goes into f? That'll go from 0 to 35. When t hits 1, this thing will hit 35, right? Pretty slick, huh? So now I could, if I had lots of parametric functions, for instance, that I was graphing all on the same axes, I could use this kind of convenient range of t, 0 to 1, 0 meaning start, 1 meaning finish. And I can adjust to all my functions so that their arguments give me the actual range that I want. Okay, does that make sense? Okay, so parametric functions. Parameter is an ungraphed, behind-the-scenes variable. And then you have, normally we'll say it this way. X is some function of t, and y is some other function of t. And we graph f of t and g of t. T is called the parameter, but it's better termed our independent variable. And then what is the dependent? The dependent is no longer a single variable. The dependent thing is ordered pairs. What you get from this function is a particular ordered pair for a particular value of t. Could be a triple. So you could have 3 functions, right? You could have a parametric function with 3 coordinates. So that's the gist. This is the gist of this exercise that you did to come up with that graph. Is this kind of it's the backbone of parametric functions. Okay, now let's flip the page over. So here, driving from Tucson to Tempe, heading northwest, Jacob comes to a straight stretch of highway shown. Final goal of this activity is to make a sketch of Jacob's distance from Maricopa as it co-varies with his distance to Casa Grande. What we mean by that is the straight line distance from the car to the town. So for instance, right now, the distance Jacob is from Maricopa is the straight line distance, like this. Kind of. Try that again. There we go. So that's the distance right now from Jacob to Maricopa, and this is the distance from Jacob to Casa Grande, right like that. Okay? So as Jacob travels the road, those distances will change. So the end goal of the activity is the graph down at the bottom, distance from Casa Grande versus distance from Maricopa. First, though, in order to do this, we want to sketch two individual graphs, one for Jacob's distance from Maricopa and one for his distance from Casa Grande. What parameter is best for the horizontal axis? All right, so I'm leaving up to you. There is a most convenient choice. So we're going to figure out what parameter are we going to use that's going to help, that would be kind of help us to make the graph of distance from Maricopa and that same parameter, distance from Casa Grande. And then based on these two graphs, we're going to put the final graph together. So again, this is the kind of the backbone or the underpinnings of what a parametric function is like, but now I'm asking you to come up with that parameter on your own. What is that? And I'll give you a hint. It's not time, okay? So you're going to come up with something that's going to be convenient here. What's going to be convenient? So you're going to brainstorm on this. You got a couple minutes to get started here.